There was, however, one odd thing about Maxwell's theory.
While it united the electric and magnetic field into one field, there was a strange thing about how relative motion was handled. Since Galileo, it was understood that fixed relative motion shouldn't affect the behavior of the laws of physics. So, for example, if I was on a train, traveling at a constant high velocity relative to the Earth, and threw a ball, the trajectories and behavior of it relative to me and everything on the train would be the same as if I was standing on the Earth, not moving. Further, if I observed this event outside the train, stationary relative to the Earth, I would see the same physics, only with the train's velocity added to all the objects on the train. This idea is encapsulated by saying that the laws of physics are invariant, or the same, for different inertial or non-accelerating frames. In Maxwell's theory, the force on a charged particle generated by a moving magnetic field was treated as arising from a different source, depending on the relative motion of the magnetic field. This is despite the fact that in both cases the strength of the force from the resultant field is the same. So, for example, if one waves a loop of wire across a magnetic bar, a force is created in the wire that can push on the electrons in the wire via the Lorentz force law, part of Maxwell's equations. However, if instead I keep the loop stationary and wave the magnetic bar to generate the exact same relative motion, the change in magnetic flux creates the force due to Faraday's law, part of Maxwell's equations. That these forces are equal is in part due to the constant speed of a wave propagating in the electromagnetic field, regardless of the relative velocity of the frame of reference. That is, the speed of light must be independent of the inertial frame. While there is some indication that Maxwell may have recognized this fact, that the speed of light was constant, it wasn't until Einstein that the constancy of the speed of light was stated and used to build up the special theory of relativity. The constancy of the speed of light explained the failure of the famous Michelson-Morley experiment to measure the effect of relative motion on the speed of light. It also suggested a startling fact, that there was no physical ether, that these electromagnetic waves were waving in a non-physical medium. With Einstein's special theory of relativity, several other important physical consequences were shown to follow. The constancy of the speed of light meant that no matter how fast or slow one was moving, the measured speed of light would be the same. Normally, when calculating the speed of an object in a moving frame of reference, one can simply add the velocity of the frame to the velocity of the object relative to the frame. For example, a ball thrown on a train with a velocity v would, if looked at from a person stationary on Earth, travel with a velocity of v plus the speed of the train. This addition of velocities didn't work for light. The profound consequences of this required that both time, length, and mass would be modified based on the velocity of the frame of reference which one inhabits. The idea that space, time, and mass could change depending on which inertial frame of reference it is observed in also demonstrated that mass was actually another form of energy. And years later, with general relativity, led to a new understanding of gravity as due to the distortion of space and time caused by mass and energy. Einstein went on to cause more problems for the standard understanding of light as waves of ether. He later explained a phenomenon known as the photoelectric effect, where when light above a certain frequency was shined on a material, it would suddenly start emitting charged particles. He explained this effect by arguing that at the smallest level, light behaves not as a wave, but as a particle with the energy and momentum of the light parceled up into quanta of light called a photon. Later, this quantum-like absorption and emission was used successfully by Niels Bohr to model how an electron in a hydrogen atom absorbed and emitted light. Only now it was the electron's orbit about the nucleus which jumped quanta-like from higher to lower orbits. These orbits were related to its energy. But the strange thing was that these orbiting distances were discrete and well defined. In fact, the whole idea of an electron orbiting moon-like about the nucleus had a well-known and serious physical problem. Since Maxwell's equations tell us that charged particles, when accelerating, which happens when something orbits another thing, will give off electromagnetic radiation, or light. That any electron actually orbiting a nucleus in this manner would radiate all its energy away and collapse into the nucleus. This fact was well understood ever since the planetary model of the atom was proposed, yet its solution had remained a mystery.